But I think that this time is okay. So
This
sorry
is
for
very good.
making
No,
you wait.
and
Let's stay at
thank
all.
you for scheduling it at a time that's also convenient for me. Thank you very much.
Okay, great. Okay, so it's now about the starting time, but still we see the people just joining. Uh, so let us wait for a couple of minutes. So those who just joined, welcome to the items curriculum, and we will start shortly. In the meantime, because we have over 200 registration for this occasion, so for the sake of the avoiding confusion, if you need to or compare to ask a question during your talk, please use the chat first. I'm just going to send you a chat message. So you should see my chat message there. So you can click if you see something red in your button, then that's the chat pane will show up. And so that I can see you. Oops. So I need to do the everybody. Yeah. Okay, you should show, you can see the chat message from me, and you can type in your question or something. I'll watch that for Robert, and so I might or might not intervene at that point, so that he could clarify at some certain point. So, all right, we just have 146 participants and counting. So just a few more minutes. Okay, thanks. Somebody just answered to my chat message. So it seems working. Okay, so yesterday I sent out a message that this is also live streamed over the YouTube. So some may just decided to just watch the YouTube live, but those who are watching through the YouTube cannot ask the questions. Anyway. Okay, so we now have the 150 people joining, so maybe it's a good timing to start the curriculum. So welcome everybody for the items curriculum. We are thrilled to have Robbert Dijkgraaf from IAS for this occasion. And so let me repeat some procedures to take for the questions. If you need to interrupt the lecture by a question or comment, please first type in the chat message so that I can direct the question to Robert or ask you to hold a question for the later. And at the end of the lecture, Robert will take question. Okay. So now I ask the Hatsuda-san to introduce the lecturer, Robbert Dijkgraaf. Please, Hatsuda-san.
Okay. Good morning in Japanese, Japanese Standard Time, and then good evening for from US or maybe the midnight in Europe. Okay. So my name is Tetsuo Hatsuda, who is a director of items, Riken items. Riken Interdisciplinary Theoretical and Mathematical Sciences program. And then we are having online colloquium every 2 months or so. And then this time we are very happy to have Professor Robbert Dijkgraaf from Princeton. So let me introduce a little bit about him. Sorry. So Professor Robbert Dijkgraaf obtained his PhD in 1989 from Utrecht University, and then he's a mathematical physicist. So his research subjects include black holes in string theory, topological string theory, supersymmetric quantum field theory, matrix models, and their interrelations. So for his great contributions to the theoretical and mathematical physics. He received Spinoza Prize in 2003. That is the highest scientific award in Netherlands, which was named after the famous Dutch philosopher Baruch de Spinoza, as far as I pronounce that correctly.
Right.
Yeah. And then Professor Dijkgraaf is also known for his love and aptitude for arts. And he also served as the president of the Royal Netherlands Academy of Arts and Sciences from 2008 to 2012. So since July 2012, he is the director of the Institute for Advanced Study and Leon Levy Professor in Princeton. In 2017, just 3 years ago, he authored a book entitled The Usefulness of Useless Knowledge, including an article with the same title by Abraham Flexner, the founding director of the Institute for Advanced Study. So this book is about the importance of curiosity-driven research in basic sciences and so forth. And the book was published from Princeton University Press and actually was translated to Japanese with the title 役に立たない科学が役に立つ in Japanese from University of Tokyo Press in this summer. So if you're interested in, you can either read the English book or if you prefer the Japanese book also. So today we will listen a beautiful connection between physics and mathematics. The title is the Unreasonable Effectiveness of Quantum Theory in Mathematics. So let's welcome Robbert. Please.
Thank you so much for this extremely kind invitation and the pleasure to actually speak to you. No, it's you already mentioned the book, and I want to thank Riken, but in particular, thank you, Hatsuda-san, for taking the initiative to translate my book. I'm very, very honored. I have it right here and on my desk, so I'm very happy to it. In fact, I want to give you a small anecdote before I start my lecture, because this book was published. Basically my co-author, Abraham Flexner, was the first director of the Institute for Advanced Study. And of course, he was quite famous by bringing Albert Einstein to the Institute. So when we published this book, I thought, that must be nice because Einstein and Flexner knew each other well. Perhaps I can have a blurb, can have a recommendation of Einstein for my book. Wouldn't that be wonderful if you publish a book and it says, highly recommended by Albert Einstein. So I thought, let me check. I have a thick book of Einstein quotations here. If there's anything about Abraham Flexner. And I saw that in the index, there was one. So I think I'm in luck. So I look into the index and I find one citation of Einstein about Flexner, who was his director. And that citation actually says, Flexner, the former director, is one of the few enemies I have here. Years ago, I conducted a revolt against him for which he fled. So then I proposed that we put on the book, Albert Einstein, a book by one of my enemies. But even that, I think, was a little bit too far. But this actually shows you, if any of you ever wants to become a director of an institute, this is your fate. But let me go back to the title of my talk, The Unreasonable Effectiveness. The unreasonable effectiveness, of course, is a wonderful saying that actually kind of started by this kind of saying of Eugene Wigner, who wrote a famous article, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And in that article, which is highly recommended, he gives an example of talking, to somebody who is interested in populations, and showing the Gaussian distribution, as you see here on your screen. And the person asks, what's that symbol over here? This funny symbol, and the mathematician said, well, it's the Greek letter pi. And then they ask, what does it mean? Well, it's the ratio of the circumference and diameter of a circle. And then the person asks, what do circles have to do with populations? So it's indeed a very deep fact that mathematics is able to capture so many of these different phenomena. And in fact, at the end of the article, Wigner writes that it's actually a miracle. It's a wonderful gift that we neither understand nor deserve. And we can only hope that this relevance of mathematics stays for the future. In fact, there's a long line of researchers speaking about this. This is Galileo, who wrote that philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language in which it's written. So in his language, you can only understand physics if you truly understand the characters in which it's been written. And let me go to another quote. This is from Arnold Sommerfeld. If you want to be a physicist, you must do three things. Study mathematics, second, study more mathematics, and third, do the same. Or here is Richard Feynman. To those who know mathematics, it's difficult to get across the real feeling of the beauty, the deepest beauty of nature. If you want to learn about nature, you have to understand the language that he speaks in. On the other hand, he also gave the quote, if all mathematics disappeared today, physics would be set back exactly 1 week. So I always thought this is a wonderful saying. And what is the right response? But the right response actually comes from a famous mathematician, Michael Atiyah, who said, that was the week that God created the world. So I would say 2-to-1 to kind of mathematics. Now, mathematics, of course, often sees itself as a Platonic science. This is other famous quote from the mathematician Jean-Pierre Serre, who said, while the other sciences search for the rules that God has chosen for this universe, we mathematicians search for the rules that even God has to obey. And if you think about David Hilbert, who had this famous list of problems that he published around the turn of the last century, one of the problems of mathematics he felt was the mathematical treatment of the axioms of physics. So just find, a full description, so to say, theory of everything of physics, in terms of the axioms and the definition that was seen as part of the problems of mathematics. And perhaps, as a final anecdote, a little anecdote that I learned from Alan Kohn, famous mathematician, a Fields medalist. He described the physicist as, he has a big bag of dirty laundry, and he goes into a village to find a place to do his laundry. And he finds a little shop, and it says laundrette, but it also says restaurant, it says cafe, it says hotel. And it's, of course, that shop is run by a mathematician. And then the physicist comes and says, can I do my laundry here, my dirty laundry? And the mathematician says, no, you cannot. But why can I not do? Well, the only thing that we sell are advertising signs. That's another response, I think, that many physicists have. There are all these wonderful symbols and things, but mathematicians are perhaps not so much interested in doing your dirty laundry. Now, I want to say there's another view of mathematics that mathematics is in some sense also an environmental science. The mathematics that we know were often created, born by studying practical problems in the natural sciences. Think of astronomy, and that really was born in terms of, gave rise to geometry in the ancient times. Or think about mechanics, how it was developed by Newton and Leibniz and others. And they, in order to do that, they had to think of calculus. Or think about how the study of symmetry led actually to modern algebra. It's quite remarkable that that in some sense studying the quintic equation in the end led to the development of modern symmetry. So the question I want to kind of ask today with you is, now, what is the natural context? If the natural context is quantum field theory, string theory, what is the right kind of mathematics that would flow out of that? Is there something like quantum mathematics? In fact, what is the role of the sciences at all in framing mathematics? Now, I want to actually come to a question that was asked by Bill Thurston. Bill Thurston, a famous mathematician, who basically asked, what is the best definition of a mathematical object? And he gave an example. Think about the derivative, something that we all know and use. And he said, well, there are many ways to look at the derivative. Now, one way is the formal definition in terms of limits, the epsilon delta definition. But you can also think of a derivative as the rate, the velocity. If you think about that, you immediately realize that you can generalize it to a function of more than one variable. It has a vector. You can also think of it as a tangent, the slope to something. So this is very natural if you have a function of more than one variable. You can think of it as an infinitesimal change. You can think of it as a discrete jump where you make the jump smaller and smaller. You also can think of it as a symbolic object that actually you can apply to different algebras, not necessarily the real numbers. Or you can think of it as the linear approximation, or you can think of it as a microscopic way of looking at functions. And then he writes at some point, there's definition number 37. He said, at some point, I needed the following definition of a derivative. I'm not reading it, but it's a very complicated definition about a Lagrangian section of the cotangent bundle. But his point is, we need all these definitions to really fully understand what the derivative is. These contexts are crucial in understanding the strength of a mathematical symbol. And for instance, there is a derivative. If you study knots, we'll see knots in a moment. There's even the concept of the derivative of a knot, where you pass from an overcrossing to an undercrossing. So derivative is a little like a diamond with many, many different facets, and all the different facets illuminate a particular element. Now, the seal of the Institute for Advanced Study says truth and beauty. And I also want to talk about the concept of beauty in mathematics and physics. Now, actually, the epigraph of a Weakness article states that this beautiful quote by Bertrand Russell, that that mathematics possesses not only truth but also supreme beauty, cold and austere. And another famous quotes. One of the famous mathematicians working here at IIS has been Hermann Weyl. And when he was asked whether he preferred truth or beauty, he was very clever. He said, I always try to unite the two, but when I had to choose, I usually chose the beautiful. Paul Dirac famously said, it's more important for our equations to be beautiful than to fit experiment. But of course, there are complementary views. I like this statement by John Wheeler, that every law of physics pushed to the extreme will be found to be statistical and approximate, not mathematically precise, perfect and precise. That's another point of view, that whatever we see, the beauty in physics, it should in some sense be an approximation, because that allows it to be improved. And then there's the statement by Francis Crick, the co-discoverer of DNA, that any theory that accounts for all the facts is wrong because some of the facts are always wrong. There's always an experimental mistake. So we have to be very, very suspicious of theories of everything. Now, if you think about beauty in mathematics, I would say there are kind of two distant flavors of beauty. One, I would say, is what I would call universal beauty. It's the beauty of vector spaces or linear algebra, of general concepts that are perhaps quite abstract. And then there is the exceptional beauty, the objects that where only few exist, like the Platonic solids or E8 or the monster group, or in physics and in string theory, Calabi-Yau manifolds. And I think we all recognize the two flavors of beauty in ourselves. It's wonderful to study the Lie group E8, but we also know that in some sense, general vector spaces are probably more useful in everyday applications. But there's something like a mathematical Wunderkammer, a cabinet, a curiosity cabinet, where we have all these exotic elements. And just to give one example of this, Kepler famously was very much in love with the Platonic solids. And he developed this famous cosmological theory when he was a very young man. We would say he was a graduate student. And he thought, that the 6 planets the orbits of the 6 planets, in particular, the ratio of their orbits, could be explained by using the fact that there are 5 platonic solids. And he built his famous model of the universe by putting the 5 platonic solids inside each other. You can do in essentially in 120 different kind of ways. And he found a prediction of the ratio of the orbits of the planets that I think was okay up to 5%. Now, we all know this is kind of nonsense, because that's not how the solar system works. But the remarkable thing is that, he actually, he himself disproved his own theory by showing that the orbits are not circles, but ellipses. When he found this result profoundly ugly. In fact, he writes somehow, in fact, many of his contemporaries criticized him because the oval, the ellipse, was, of course, not as beautiful and singular and special as the circle. And in fact, that he somehow cleaned this is what he writes to Tycho Brahe's assistant, that he basically tried to clean the Augean stables, but he, in his own words, he added a barrow full of shit in the stable. So he felt this was like really, really ugly result. It was true, but it's really ugly. Now, of course, we know that these equations, these ellipses are conics, and so are part by a beautiful theory given by Newton. Now, if we move forward in history and we go to the 1960s, we find a very different situation. In the 1960s, mathematics really went in a different direction. It's the time of the Bourbaki seminar, a very abstract mathematics, a time where the famous slogan of the Bourbakis, this group of French mathematicians that built up mathematics from the bottom up, was that structures are the weapons of the mathematician. Well, in physics, in fact, this was the time of the S-matrix theory, and it was also the end of reductionism. Steve Chu famously said that the aristocratic structure of physics, as governed by theories, by quantum electrodynamics, should be replaced by a revolutionary character. Every particle should have equal treatment. So basically, physicists gave up on a mathematical description, and mathematicians gave up on the relation with physics. To give an example, this is a letter of John Wheeler written to Richard Feynman, where he invited him to a conference to talk to mathematicians and explain to mathematicians what was happening in physics. And Feynman had a very short answer. I'm not interested in what today's mathematicians find interesting, and he didn't want to come. In fact, Freeman Dyson, who unfortunately passed away this year, the wonderful mathematical physicist, wrote in 1972 that the marriage between physics and mathematics, between mathematics and physics, that was so enormously fruitful in past centuries, has ended in divorce. Now, I would say these are famous last words, because right at that moment, this kind of black box of particle physics that in the 1960s people thought would never be opened, that in fact perhaps you shouldn't open, could be opened, and inside it, I would like to say, was a really tiny formula. So this is the formula of the standard model of elementary particle physics, used very clever and succinct notation. But all the elements that you see there, gauge fields, spinors, covariant derivatives, are actually very natural objects in the language of differential geometry and topology. So you could explain the standard model formula to mathematicians, even if they have no knowledge of physics. And of course, we know that physics is built up by these elementary processes. And these rules allow us to calculate these objects in incredible details. In fact, you can somehow trace the beginning of that dialogue to a famous seminar that started in the 1970s, early 1970s in Stony Brook, New York. It was run by the physicist C.N. Yang and the mathematician Jim Simons. And they literally built up a dictionary between the objects that you see in gauge fields, so in physics, and that you see in topology, in differential topology. And they actually noticed that actually exactly the same objects were used on both sides of that dialogue. So this is like a cartoon where I kind of summarize that development at some point. No, so in the 1960s, there are all these exciting developments in physics and math. And 30 years later, actually the things turned around, and now the physicists are studying the mathematics, and mathematics are studying the physicists. So this is my commentary on the progress in science. Now, we talked about beauty in mathematics, but there's also beauty in physics. And I want to also distinguish two different strands of beauty in physics. And so the question is really, where do you find beauty and where do you find the opposite, say garbage? Now, I would say particle physicists would typically say that the real beauty is found at the smaller scales. The world is complicated, but if you go to the level of the standard model, then you find elegance and simple formulas. On the other hand, if you condense matter physicists, you would argue exactly the opposite. You would say that if you want to understand, say, a glass of water, or thermodynamics of a system, or hydrodynamics, these are very elegant formulas. But actually studying the individual motions of 10 to the 24 molecules is a very messy and complicated system. So beauty appears at the very large. So in some sense, I think this is reflected in the two main theoretical ideas we have. Now we have gravity, which is our description of the physics at large scales, and we have quantum mechanics as the physics at small scales. And we notice that they're both very beautiful, but in a very different concept. In fact, the kind of mathematics they use are quite opposite. You can say that gravity uses the mathematics of geometry, and quantum mechanics uses the mathematics of algebra. In fact, it is another way to look at mathematics. Instead of universal and exceptional, you can think of, are you a more visual person? Are you using your right brain functions? Do you like to turn things around in your mind? Or are you more a logical person? Do you like to think of mathematics as a sequence of steps? Then you probably love algebra more. And so we see both flavors are also used in mathematics. And I think the exciting thing is that we know there are links between these two sides. Basically, we are connecting the two hemispheres of our brain. For instance, the process of quantization is taking essentially a classical object, so geometrical object, and moving it towards the side of algebra. Giving it abstract qualities as probability amplitudes. And I will show somehow that there is also an interesting arrow going the other way. There is a concept where geometry actually can also emerge out of algebraic systems. So this is the equivalent essentially of thermodynamics emerging out of the description of a microscopic statistical mechanical ensemble. And in some sense, I think we're looking for a synthesis. So I would say quantum geometry or string theory or fully understand quantum physics would combine both the geometry and the algebra. Now, if we think about, if we move into the quantum area, there are some loss and gains. Clearly, if you're a student and you first learn about quantum mechanics, it's very beautiful, it's very elegant, but you also struggle with certain things. Now, if you have a classical mechanical system, of course, it's somehow very straightforward to understand. There's some phase space, there's some variables, and you have a dynamical system that moves on that phase space. In quantum mechanics, the Heisenberg uncertainty principle basically tells us that that phase space has disappeared. The variables start to no longer commute. I myself like very much the quote of Wolfgang Pauli that he wrote to Werner Heisenberg just 3 weeks after Heisenberg discovered his uncertainty principle. And Wolfgang Pauli says, well, I understand what you're doing. You can see the world with the pi, so think in terms of momentum. One can see the world with the qi, thinks in terms of position. But if one opens both eyes, then one becomes crazy. And I think we all share that experience learning quantum mechanics. And I think that's somehow the thing that we know. If you want to be a quantum mathematician, you will have to look at the world with both your left and your right eye. And of course, we know there are other things that quantum theory does. It introduces, essentially makes everything in terms of linear spaces. It makes superpositions and probabilities. Now, if you think about classical mechanics, you can think of it in some sense as all of it as classical physics, as in some sense finding the shortest path between 2 points. So we know there's the action principle that will tell us, how to find the geodesic, or in general the solution of any dynamical system. However, if you go to quantum mechanics, Feynman showed us, Feynman and Dirac, that we can think of this as a sum over histories, as a path integral. As in some sense, quantum mechanics is probing everything at the same time. It took a long time for physicists to realize the power of this way of looking at things, but actually it very much is in the same spirit of what happens in modern mathematics. Now, modern mathematics, you don't look at one particular object, you look at the category of all possible objects. In fact, you not only look at the object, you look at their mutual relations, or the relations among the relations, or etc., etc. So quantum theory is very well set up for modern mathematics. In fact, but still there are some very strange things. For instance, if we think about a quantum theory, you can somehow, it's trying to combine quantum mechanics and geometry. So we think of a quantum field theory as somehow local description. I think it's almost a bucket of paint that I can put on every possible space-time manifold, and I get a quantum field theory. But one thing we have realized, that there are these kind of wonderful dualities. So you can have two classical field theories that you can both study in a quantum version. And there could be a very complicated moduli space of interpolating quantum field theories. So it's possible to go from one classical description to another classical description. There's one classical limit on one side, another dual classical limit on the other side. So it's not enough to think in terms of these quantization of classical objects. A quantum field theory is something much more complicated. Again, in quantum field theories, there are two ways to look at it in a more axiomatic definition. You can think it in terms of the algebra, in terms of the local operators, or you can think of it in terms of the geometry, thinking of the quantum field theory and cutting your space-time manifold in pieces and see how the various components glue together. Which I think, all in some sense, I think we can only see that, our approach right now to quantum theories is very much to, somehow the approach to the derivative, in the sense we have all these different perspectives, but we're still lacking, I would say, a universal valid description. Now, let me give you a few examples how the application of quantum intuition is extremely powerful in mathematics. So my first example is from particle physics. So I want to say a few words about knot theory. So mathematics try to categorize all possible knots. And I would say, there is a nice way to look at it, which goes to, again, John Wheeler and Feynman. Now, Wheeler describes this, or Feynman actually describes this in his Nobel Prize lecture, that Wheeler gives him a call in the middle of the night and says, Feynman, why do all electrons have the same charge and the same mass? And Wheeler says that's because there's only one electron. All the electrons are the same. And this is his picture. If this is space-time and this is electron, we expect it to go forward in space-time. But suppose, I'm sorry, this my slide is actually the background. I'm not sure what happened to the background. But if you allow the particle to kind of go in a very complicated loop, I'm sorry it's not visible right now, and you look at it, you can see that there are many particles and antiparticles if you slice the knot in the middle. In fact, you can even have particles beginning and ending, or just going up in time. So the modern point of view is that you can think of a knot as a trajectory of a particle in space-time, in this case, 2 space and 1 time directions. And then the rules of quantum mechanics would actually associate to this geometrical object a number, which is the probability amplitude. And in fact, if you have Feynman diagrams, you could, for each individual Feynman diagram, you can compute an individual amplitude for the knot invariant. And so in an abstract way, you can say what quantum mechanics does. It takes a knot and associated to it a knot invariant. And this has turned out to be an extremely powerful principle in generating knot invariants. And in fact, several Fields medals were earned by mathematicians, applying these ideas. My second example is from string theory, and that has to do with mirror symmetry and enumerative geometry. So enumerative geometry is studying essentially curves on complex manifolds. The most famous is the quintic. So it's this particular equation of 5 variables in projective space. So it's a complex 3-dimensional space. It's in fact a space that allows for a solution of Einstein's equation. And the mathematicians were interested in studying the curves on this manifold. And you can have a curve of a degree d if these 5 variables each are polynomials of degree d in an auxiliary variable z. So there's a number, n of d, which is the number of curves of degree d. Now the first to do is degree 1, so the number of lines. This is a number, 2,875, that was first calculated in the 19th century. It's only in the 1980s that mathematicians computed the number of conics, which is a much larger number, 609,250. And if you compute the number of cubics, the number is even much larger. It's 300,000, basically 300 million. And there's a nice story behind this particular number, because actually I do want to, if you allow me, change the layout of this one variable. So there's a nice story behind that number, because actually the physicists asked the mathematicians to calculate it, and they came with a number, but this was not this number. And then the physicist said, are you sure you didn't make a mistake in your computer code? Because it was a very complicated calculation. And the mathematicians went back to the computer code, they found a mistake, and they corrected it, and then they came with this number. But of course, they were wondering, how did the physicists know that they did make a mistake? And they knew because, in fact, the physicists had all the numbers. Now, this is a problem that grows exponentially in difficulty. So it took, to even compute N4 or N5 was almost unimaginable for the mathematicians. So when finally they were presented with this list, this was like the most shocking thing. It's like somebody comes down and hands you the solution to every question that you ever would like to ask. So what did the physicists know that the mathematicians did not know? Well, they were actually using the path integral. Now, if you study a string moving in that particular geometry, by the sum over histories, that physical amplitude is computing all possible paths, and so essentially computing all the possible degrees. In fact, it creates a generating function for all these numbers. And it was this particular function that the physicists were able to compute. In fact, they used a very clever trick, one of these dualities, that computing this number on the original manifold could be translated in a dual calculation using a dual quantum field theory, which actually was much easier to calculate. So not only did they have a way to summarize all the numbers, they also had a very clever trick to calculate this. Now, my third example actually is much more profound, which is studying quantum gravity. Now, if you study quantum gravity, the space times that you study themselves become quantum objects. So in some sense, we're thinking about the abstract problem of summing over all possible geometries, which usually is called like space-time foam. And so we think in some sense that classical geometry, it can be kind of deformed, it can be studied in string theory, but there's also something like quantum geometry, which should not be geometry. Quantum geometry should be something that underlies geometry. Essentially what physics tells us, that there is something more fundamental than space and time. Now this is rather baffling to mathematicians because they think of geometry and spaces as the most fundamental objects are there. So what is there? It's almost like you can see the individual pixels of your space. Well, string theory have given us very interesting examples. So in string theory, we not only have closed strings, we just saw them appearing in enumerative geometry, but you can also have open strings, which are essentially where the endpoints end on a submanifold that string theory is called a brane. And in fact, you can have many of these branes. And if you study sets of these branes, the open strings in a very natural way become a non-abelian gauge field. So you're led to study non-abelian gauge structures. Now, another crazy duality that's, in some sense, one of the great new insights in string theory is that there's again a duality that relates collections of these branes, so these collections of these large N gauge fields, with curved space-times, closed strings. So there should be a way in which studying systems of large symmetry groups should be equivalent to studying quantum geometries. Now, the intuition, the physics intuition is if you have gauge fields, you can write their perturbative expansions, their Feynman diagrams in terms of these ribbon diagrams. And if you have an open string diagram with many features, then actually it can, in some sense, be, if you have strong coupling effects, can be replaced by a closed string worldsheet. Now, in the most spectacular application of this came through the ADS-CFT correspondence, which is this phenomenal effect that we have been studying for almost 25 years now in physics, that tells us that studying a quantum system on the boundary of a space-time is equivalent to studying the interior of that space-time using gravity, using general relativity. And you can even think of a kind of a baby example of this phenomena, something that I like very much, which are kind of matrix models. If you take an ensemble of n by n matrices, in fact, was introduced by Eugene Wigner when he was studying in the 1940s and 50s, Hamiltonians or very large systems, then we know that the dynamics of these eigenvalues in the limit where the rank of the matrix become very large, the density of eigenvalues actually produces a continuous distribution and actually creates a space. In this case, it creates a circle. And so the emergence of that circle in the large N limit is an example of an emergent geometry that we now have had many other examples. So I think one thing that physics is predicting, there's a way, we have seen there's a way to go from geometry to algebra using quantization, but there's also a way to go from algebra to geometry by looking at quantum systems with many degrees of freedom. So if you have many degrees of freedom, a quantum system, then we expect that it's being captured, the physics is being captured by geometry. And geometry in some sense is equivalent to algebra in this particular framework. So basically we're saying if you look at quantum physics from a mathematical point of view, again, you can look with your left eye and your right eye. You can see geometry, you can see algebra. In geometry, we have the language of Riemannian geometry, of minimal surfaces, of black holes, of all of that. In algebra, we'll use the language of vector bundles, matrix models, and gauge theories. And so in some sense, we have to unify these two different concepts to fully understand quantum geometry. And this dictionary between has many very exciting components. Recently, we have seen some applications of this in the study of quantum black holes. Now, this is a picture, again, from John Wheeler that he made in the 1970s when he first introduced the concept it from bit. So Wheeler had this idea that geometry is basically being knitted together by taking quantum bits and entangle them, and that we perhaps should space-time as being created out of quantum information. Now, so one place we know that this is extremely relevant is in the study of black holes. So if you again look at black holes from these 2 points of view, they're quite opposite. From a gravitational point of view, a black hole is the simplest object that you can have. It's just a hole in space. It's literally the simplest possible object. From a quantum perspective, a black hole is the most complex object there is. In fact, it's the most compact way to store quantum information. We think that the information content of a black hole is equal, its so-called geometric entropy using the Bekenstein-Hawking formula, is equal to the area of the horizon measured in Planckian units. So it's incredibly powerful. All the information in the internet could be stored in a black hole that's much, much smaller than the smallest elementary particles that we know. So we expect that, again, gravity and quantum mechanics should have this kind of dual formulation. And we are exploring currently these possible connections. For instance, in gravity, you can think of gravity has this notion of locality. And in fact, one way to connect two possible points in space-time is to build a wormhole connecting it, as Einstein showed actually in the 1930s when he was a professor here at the Institute of Advanced Study in 1935. But we also know that in quantum mechanics, we can entangle quantum bits. And one of the recent insights is that these two contributions of Einstein, both introduced in the same year, 1935, could actually be two equivalent components of the same idea. That is to say, the locality that we build in gravity is a reflection of the entanglement of quantum bits. Now, I would say this is all very confusing. It's very tantalizing, but you have seen a pattern during my talk. All the examples I gave, I said just the left-hand side, there's a right-hand side. I'm giving you examples how to translate one concept to the other. So what we basically are doing, we're seeing these two languages of physics and mathematics. And what we are doing now is that we are building dictionaries to translate concept from one side to the other. And they're almost like metaphors. It's like you find a Rosetta Stone, the famous archaeological find that allowed archaeologists to translate the hieroglyphs of the Egyptian language, because there was also a Greek text there. In fact, there's a wonderful quote by, but what I would like to say is that although there is these translations between mathematics and physics, it looks almost that, physics and mathematics do not commute. That is to say, physics gives us intuition, mathematics gives us rigor. It's almost impossible to look at the world both with the intuition of physics and with mathematical rigor at the same time. So there have been many examples of problems that came out of physics. So I mentioned the examples of mirror symmetry that are now proven in mathematics. But mathematicians have not straightened the logic of physics. They've just taken the results from physics, say, well, that's a nice conjecture, and then actually gave a completely different mathematical proof. So to say, they haven't done the dirty laundry of physicists, namely straightening out all these fuzzy concepts that we use in physics. But we have these Rosetta Stones. We are able to translate to other. Here's the quote of André Weil, another famous IES mathematician. He said that you use these kind of metaphors, and he was famous in developing this program, what's called arithmetic geometry, basically translating between number theory and geometry at the same time. So there's a long tradition in mathematics of having different points of view. But I would say there is a deeper question here. There are basically two ways to look at the world. Here on the right hand side you see a nice globe. That's a globally defined object. That's you can see exactly that's our planet. But you can also buy an atlas, which you see on the left hand side, and then you have individual maps, and you have ways how to go from one map to the other map. So the question is, if we look at the current understanding of quantum physics, is that we have all these different ideas and all these different fields, and sometimes they overlap, and sometimes we are able to make a translation from one to the other. It's like we have to learn all these different languages in order to describe parts of the world. But of course, the biggest question is there some way to unify all of this? Is there a global point of view in quantum physics where all these bizarre dualities, all these different mathematical ideas are being used? And is there something like we would call quantum mathematics? And then the question is, if this exists, well, we know that the classical world has given us terrific mathematical concepts, calculus, geometry, algebra. We use it every day. But I feel this is only describing the classical world, and we know the classical world is not the real world. The real world is quantum mechanics. So the question is, if mathematicians could think like an elementary particle, what would be the mathematical concepts that would appear? Would it be still the same concept that we are using in the classical world, lines and curves and algebra and derivatives? Or are there completely new quantum mathematical concepts that we have to discover? I think there are many, many indications that our mathematical language is not sufficient to fully capture what's happening in quantum physics. So I think this is extremely exciting, because we have seen that mathematics is unreasonably effective in describing physics. But physics is also unreasonably effective in developing new mathematics. So my prediction is that perhaps in the next century, we have many new concepts in mathematics that we can learn and we can apply that will actually allow us to really capture what's going on in physics. But up to now, in fact, we have to work with all these partial answers. But this is, I think, where we would like to move to. So I would say thank you very much. And since it's already Thursday in Japan, happy Thanksgiving.
Okay, thank you very much, Robert, for very beautiful and inspiring talk. Okay, so now I think we can take questions. If you have questions, raise your hand so that I can see you, or type in the chat. Okay, so there's some question from we call Chacha-san. So maybe it's long. So why don't you just unmute and ask the question, the comment yourself?
Sorry. Thank you so much for your talk. It was very interesting. Actually, I'm speaking here as a mathematician. I work in number theory, and I completely agree that there are a lot of new concepts, mathematical concepts, which are not unified, as you said. So, I mean, they are scattered. I mean, they are scattered all around, and that makes it difficult to apply them to solve some certain real problems. I mean, like physical or biological problems. And yeah, of course, I mean, we need interactions among us. I mean, among mathematicians and also physicists. So, seeing from your examples, actually, I came up with a question. So did you mean that there are a lot of mathematical questions which have physical background that mathematicians themselves do not know of them. And but actually the physics behind those questions actually tell us a way to solve the problem. So that is some of these problems actually are easier to solve by physicists because they know of the background.
I think you're quite right. So thank you for your question. I think, this indeed, the examples that I showed, like the ones from knot theory or enumerative geometry, are exactly of that kind. I think, it's for physicists, it would be very natural to study, for instance, these curves of all degrees at the same time, because that's what quantum mechanics is about. However, for mathematics, that would not be a natural thing to do. You would study them one by one. Why would you add them? What would it add to? I think, and what would the variable be? You produce this function of one variable. What's the significance of that variable? Well, in some sense, it's Planck's constant. But what does Planck's constant mean, right? So I think that was a very natural. It's a step that, of course, it took physics more than a century of struggle to develop, quantum theory. So I think this is an insight. This is a context that was very natural. So in that sense, I would like to say some mathematical problems are the solution presents itself if you provide the right context, because the context actually allows you to look at the problem from a different perspective. And then, of course, I think you can generalize. One of the wonderful things in this particular area is that mathematicians have taken that concept and generalized it, in ways in which physicists wouldn't even thought of. So it's the same as the derivative. The derivative was very natural for Newton, but he didn't think of functions of infinite variables, or there's so many other ways in which you can push that concept. I think I think the interaction goes both ways. If you want to have a more symmetric point of view, I think some mathematical areas are also a context for physical questions, right? Because you can,
right,
from a mathematical point of view. So to give an example, mathematicians develop category theory as a very natural thing. So they said, well, it's not enough to look at the objects. You have the relations and the relation among the relations. And I know initially physicists said, well, we don't need all these extra steps because they're not necessary. And then they start thinking about cutting a manifold in half and then cutting that again, and you have corners. And then the question, what's on the corner? Or you cut it even more. And then you realize you need all the abstractions of higher category theory. So that's an example, I think, where the mathematical context brought the physics. And finally, I think you're quite right. I mean, this is a little bit speculative, but if you think about some of the natural sciences where mathematics has not been very productive, so I would say biology is a good example.
Yeah, you're right. I agree.
Ideally, just as the interaction of mathematics with physics gave rise to calculus and analysis, you might hope that the interaction of mathematics with biology gives, again, a completely different language. I think it's very arrogant to assume that all the interesting mathematical concepts have been discovered in the year 2020, right? We're just beginning in developing mathematics.
Yeah,
So I think it's one of the many ways in which math develops. It develops by introspection and studying it inside, but it also develops by the outside view of the natural sciences.
Thank you so much. That was very clear. I completely agree with you. Thank you.
Okay, so thank you, Chacha, for the question. And there's a question on the chat from Itaru Kitayama. So the question is, does the physics explored at the International Linear Collider still interest you?
Yes, it does, very much. So, well, of course, if you see all these wonderful examples of quantum physics, it's very important to realize that quantum mechanics, quantum physics wasn't developed by introspection. It was only developed because the very, very direct confrontation with the experimental results. So I think, we have to be extremely careful to think that we fully understand, or even the standard model, or even the basic rules of quantum physics. And we know that basically with each new experiment, there's a big surprise. Nature seems to be much more subtle and interesting and rich and beautiful than we expect. And so I think building the next collider and the ILC would be a wonderful next step. Is absolutely crucial in pushing the experimental part. I think it's very important to emphasize, from Kepler to the standard model, that the really productive ideas from physics often came from the experimental results. And so on the other hand, this talk was more about interaction with mathematics. But I think actually, if you see how this very beautiful interaction between mathematics and physics was rediscovered in the 1970s, this was only because of the spectacular results in particle physics. The experimental results in particle physics showed that actually we were on the right track with the standard model. So yes, definitely.
Thank you.
Thank you. Okay, Kitayama-san, if you have some follow-up questions, if not, let's move on to the other questions. Okay, go ahead, Hatsuda-san.
So it's I have two questions. One is that you said that in the 1970s there is a huge interaction between physics and mathematics, like Young and Simons and so forth.
Yes.
And then Dyson said that somehow it is diverse, but it's not actually. That there is lots of activities going on right now. But how do you accelerate this kind of interaction, or do you don't have to? It's spontaneous, or it's better to promote something? That's my question. And what do you do in Princeton, for example?
Well, I think actually, I think we have to actively encourage it. I think, and I think what actually has happened over the last, I would say, almost decades, is that I see particularly many of the younger physicists and mathematicians, they're like bilingual. They understand both sides, and they kind of work in the middle. And in fact, I think, there's somehow a field emerging that, we can call it mathematical physics or physical mathematics. I mean, it's a little bit of both. It's studying physical models, but not necessarily the physical model that describes reality, but, in some sense it's exploring the space of all physical models and using all possible mathematical views on this. So I think, it's very important that this field is being developed. It's more than a bridge. I think it's really a new space that fills the gap. And I think what we need to do is to make sure that you can have a fruitful career in that area. I don't think that all physicists should move there, all mathematicians. Clearly, they should not. I strongly believe in distribution of labor. So we should do physics, we do math. But I think there is need for this, to foster this intermediate area and makes, it in some sense, it struggles a little bit from any cross-disciplinary research area that, it's seen as not in the center from both directions. But I think it is its own center. And I noticed here at IES that we have many people who are working in both fields. And the way we address this actually is by telling particular our young postdocs that they should be able to set up their own research area, their own research direction. So I think actually empowering particular young people, to pick their own fields. And in the end, I think, the ultimate arbiter of success is whether there are, interesting results coming out of this. But I think we need some people who need to be bilingual. And I think we have a long history of this also in physics. Also in physics, we have seen very fruitful interactions between various branches of physics, like condensed matter and particle physics. And I think we benefited from people who were bilingual, were able to translate. So I think this is one of the most, if you think about a research area that has been productive, I would say in the last 50 years, where we have continuous seen interesting results. This kind of quantum mathematics, physics-inspired mathematics, mathematical-inspired physics, has given very solid returns on investment. So I think any research organization should create some space for that particular branch of science.
Okay, thank you very much. Yeah. Okay, so there are other questions, I think.
Yes, I think Tim Henke has a questions. Could you unmute yourself and then ask questions?
Yes, hello. Thank you for your talk. It was very interesting. I was wondering if what do you believe in terms of path integrals? If you expect that they will eventually be rigorously understood as a mathematical object, or that we will understand them eventually as a heuristic, which has no real rigorous counterpart.
Well, I mean, obviously, there are some very limited contexts where the path integral will make sense, but I actually hope that we will not make sense of them rigorously. And my reason is that, if we, for instance, want to think about quantum gauge theories as a path integral in terms of, the path integral is very well set up. And of course, you can study it on the computer, and it's in a lattice approximation, does make sense. But we know by studying these quantum dualities that, for instance, you would have, the path integral would have quite magical properties, that, the path integral of a gauge field with one gauge group and representations should be equivalent to a path integral with other gauge groups and other representations. So it could be that in some sense the path integral, suitably understood, has this wonderful property, just as a Fourier transform or something. But I think, it would be much more interesting if even understanding, I would say, the standard quantum field theories will involve an object that has different degrees of freedom, that is not just a path integral over the classical fields, but has a more in that sense, that path integrals themselves could in the end be something like the semi-classical approximation to another object. So that they could make sense as a heuristic, they could make sense in some kind of series approximation. But I ideally hope, and I fully actually expect, that final understanding of quantum field theories will bring in another set of variables, and that studying in them in terms of just quantizing in another very imaginative way, the classical variables will not be enough.
Thank you very much. It was a fascinating answer.
Okay, so for the questions, maybe Kunihiro-san. You are raising your hand, Kunihiro-san.
Yes, thank you very much. And yeah, it was very fascinating colloquium. And my question is about the role of the scales. And in physics, the scales play a significant role. And actually, in quantum mechanics, we have found the distinction between the small world and the large world. And so, and actually the some exact theory or which may be described by geometry may be reduced to something, yes, effective theory. So my question is, how do you incorporate such scales in your geometrical or mathematical world or languages?
Yeah, that actually is a fascinating question because, of course, one of the crucial, I would say, perhaps, not only in physics but in the sciences in general, we know that we always study models with an extra parameter, which is this kind of scaling dimension that is part of it. Now, so the question is, how in the end will this translate into mathematics? Do we'll get mathematics with a scale built into it? We don't really know, I would say, but one thing we have seen, of course, is certainly in this concept of quantum geometry and holography, that the renormalization group scale, in some sense, is actually turning into a space-like dimension in this kind of extended geometry. So that's one surprising connection. So one surprising connection is that the scale plays the role of an extra dimension. Then there is the issue of thinking of moving in the various scales. As such, part of this could also be that what we see in all these examples is that certainly when geometry emerges out of a quantum system, there is also a variable, because the variable is the number of degrees of freedom, right? So we always have these, think again by NBN matrices or something. So then the rank n and somehow plays the role of the scale. It sets the size of the quantum fluctuations. So this suggests that at least some of the mathematical objects might have an integer associated to them, and there is it's not one geometrical object or one, mathematical object, but it's a whole series kind of labeled by this kind of quantum numbers. The question is that a universal phenomena, or is it a little bit like Lie groups where you have series, but you also have isolated items? In fact, we know there are certain quantum systems where essentially h bar is quantized. So there is no classical limit. So it's just one object, one point. And thinking of it in terms of scales or quantization doesn't even make sense. So I actually have no idea. So we ideally would have a landscape of all possible quantum objects that we would then be able to translate into a landscape of all mathematical descriptions. I think your question is very, very pertinent. Again, we have some very limited answers. But you're right to point out that this is perhaps the biggest insight that physics brings. That instead of studying the world at once, you study it in all these different layers at all the different scales. And then it's almost like our maps in the atlas. You find ways to translate from one layer to another layer. I would say this is a very deep concept in physics that hasn't really fully penetrated mathematics. So I think that's another challenge for mathematicians, to basically think in terms of the renormalization group.
Thank you very much. And actually, I have another question. Can I?
Yes.
So the new experiences in science or our everyday experiences bring some physics or some mathematics, maybe. I mean that how do you incorporate also the information or entropy, or such an incorporation may extend your manifolds? Yeah, that's my question.
Well, to say one thing, so this is actually something which is literally happening right now. I think what we are learning is to study information, perhaps more precise, to study quantum information the right language to describe it is actually, or one language to capture information is geometry. So the remarkable thing is that, using these translations, that thinking about quantum information and all the concepts of entropy and entanglement can be captured actually by Einstein gravity. That's the most remarkable thing I feel. So that means that there is a new view of information itself, which is geometrical. In some sense, you can find black holes in a metaphorical sense, also if you study a quantum computer. Now, your question is, information is everywhere. We not only study it in quantum systems. So does that mean that we can use the theory of general relativity to understand other instances of information? I think that's very, very tempting. No, certainly if we move into the area of quantum computers, this will be quite relevant. And I think, if you speculate this point, if there is a fundamental theory out of which all of this will emerge, what could it be? Then thinking in terms of just bare information as perhaps something that's even underlying geometry, space, and time, and algebra is a tantalizing concept, I think, but I think, again, what we learn through these dictionaries, that also we do not fully appreciate the richness of the concept inside studying information. So I think that's one of the lessons. So these arrows always go two directions. I think, there are studying the relation with geometry and gravity has given completely new perspectives on information, and perhaps that's in the end, if you understand it in a really deep way, perhaps that is the so to say the theory of everything. I've no idea.
Thank you very much.
Okay, so next question from Hiroyuki Ochiai from the chat is, should a mathematician have better be or is recommended to be bilingual? I think it's in the sense of the physics and mathematics. So, or finding following just a translator between math and physics is not.
Well, I think, there's always this challenge that it's very difficult to be completely bilingual, and usually you have a mother tongue and you start learning one language. But I would say the argument that Bill Thurston made, the example I gave for thinking about the derivative, even in mathematics itself, it's extremely productive to have these various perspectives on the same object. If you only can think of a derivative in terms of the epsilon delta definition, it would be very, very hard to do mathematics. So it's I think you just as you're learning about different cultures and different languages enriches your experience. I think we should try to learn these other languages. I think mathematicians definitely try in their education to learn both geometry and algebra and statistics and analysis. So I think studying physics should be a very natural other language. But I think to be honest, you can never be completely fluent in all these languages. So now sometimes I think it's good enough to if you should at least be at the level where you understand your translation, right? But it's very important that you at least are able to start a conversation with your colleagues that are in neighboring fields. It's impossible, I'm quite interested, say, in number theory. I'll never become a number theorist. I'm simply will never be able to learn the intricacies, but I think some kind of a general understanding of these disciplines is a great advantage. And sometimes there's a folk theorem that some of you might relate to this, that, all of us, when we went to university and we learned various fields, there was always one subject that we skipped, that we thought, well, I'm not interested in that. And the folk theorem is that that's exactly the subject you will need in your research. And this happened to me several times. So, so if it's not good to have a blind spot. So.
Okay, thank you. Okay, so for the next question, I ask Kyogo Kawaguchi for the question. Kawaguchi-san, go ahead.
Hello, can you hear me?
Yes, I can hear you.
Hi, I'm Kyogo. That was a very nice talk. Thank you very much. So, as a biophysicist, I can't really help but noticing that many problems in natural science that we face cannot really reduce to beautiful problems in math. And you had a really nice example about the population fitting nicely with the Gaussian, but that may be the extent of math that we can actually utilize in understanding the distribution of population. So my question, or one of the puzzles that I have, is why is it that some specific problems about the universe or the particle physics reduce to such beautiful math, and some others don't? So would you say that the other problems, if it becomes like more sophisticated and we have understanding more experimentally or like more theoretically, will it also reduce or like kind of flourish into new math and beautiful math? Or what's your perspective?
Well, it's a very good question, but it's good to realize, as I gave the example, that when people thought about particle physics in the 1960s, it was a bit like biologists now look at their system. Now, there were millions of particles and they were all very complicated and it was a big mess. And in fact, as I said, the theory, the idea at that point was there is no theory. There is no elegant mathematics. That was in some sense the rule. And then it turns out that actually they were totally wrong. So you have to be very careful to say that there isn't mathematics because, for one, the mathematical toolbox that we have might be too limited. So I think in many complex systems, when you think of millions and millions of variables, we might just lack the language. We might lack the concepts to capture structures of that complexity. But they might still be there. I mean, there are still pretty remarkable things going on in biology, that actually shows there is a system behind it. I have no idea how we will explore these. Now, it could be, for instance, that by using smart AI algorithms or machine learning or something, we discover certain structures that the human mind is not able to capture. Also, what we call beautiful mathematics. Now, it's almost like beauty in art. Now, if there's a revolution in art, like you go to abstract painting, not everybody immediately thought of that as being beautiful. Now, it's a little bit of an acquired taste. And actually, Feynman has a wonderful way to express it. He says, you have a beautiful theory, and then there's an experiment that destroys it. And it becomes more ugly and even more ugly. But at some point, the whole thing starts to hang together again. And there is beauty, but it's a new kind of beauty. It's an acquired taste. And in the end, I think we think of it as a deeper beauty because it explains more. I mean, in some sense, you can almost define beauty in science in terms of its explanatory power. I joke, it's basically the amount of explanation per symbol is in some sense the strength of the equation, why we find an equation very beautiful. So that is also something that we have to keep in mind. And so perhaps in biology, we might be in the situation of studying populations and not having thought of Gaussians, perhaps not even thought about integrals, perhaps not even thought about real numbers. And so we still have to develop these concepts, but we see certain patterns. And I think we have to study these patterns. And I think the great hope is, in particular, I think, in the coming century, we'll be exploring areas in science of great, great complexity. Now we have massive data sets, we have massive computational power. Perhaps hidden in this great complexity, there is some elegant structure. but we're just lacking the language, the tools to find it. And I think, you know, an optimistic view is that we are a little bit like physics, looking at the stars and the planets, and not yet have discovered the universal law of gravity, and not yet discovered calculus. In fact, I would say, to make a final remark, that consistently, whenever we approach a new area in science, a new mathematical language has developed. That's almost it happens all the time. Sometimes the mathematical language is already there, but I think in most cases it's not. It has to be developed. So I'm sure there is beautiful math in the life sciences too.
Okay, thank you. I'll try to hold that optimism.
Okay, thank you. And perhaps this could be the last question. Okay, Shundu, go ahead, the last question.
Oh, hello.
Hello.
Yes, we can
Oh,
hear.
yeah. Very honored to talk to you, Professor. Well, my question is that, well, we all know that studying physics, we have somewhat like two directions. One, for example, we could goes from string theory as a starting point, and we use something like the string landscape or some holographic description to approach some low energy effective field theory like QCD or super Yang-Mills. But it seems if we want to go the opposite side, for example, we want to go from a QCD, well, from a low energy theory to some more complete high energy theory. This seems to be there really lack of such approaches. Why could this sort of things actually happen is my question.
I think that's a very good question. So to phrase it, you know, there's a top-down approach, thinking about a working theory of quantum gravity, and then trying to make contact with reality. But why not start with what we know and try to move bottom up? So I think part of this, a possible strategy could be to see whether we can take our theories that we understand and know, and we can reformulate them, or can look at it in a different way. And you know, one of my colleagues here, Nima Akhani Hamed, has this point of view. So he looks at scattering amplitudes, and he knows that even in this well-known physics, there are many phenomena that we do not understand. So, you know, in some sense, you know, if you want to move forward, sometimes it helps to develop a new perspective on something that's well known. It's not guaranteed that this is the right way to generalize. But I think there are many elements in even, you know, the well understood quantum field theories which are not well understood. And as I said, the fact that, you know, even for a non-abelian gate theory, we still not have a mathematical rigorous formulation. As you said, it might not even exist. Perhaps we need to think about it differently. Clearly, the theory is much cleverer than the Feynman diagram approach. So even that theory can be reformulated. And I know Nima likes to give the example of classical mechanics, that you can, you know, reformulate in terms of a Hamiltonian framework. Why would you do this? You know, it's completely equivalent to the Newtonian framework. But of course, it's a much natural way to quantize, right? So if physicists had all understood the Hamiltonian approach, then quantum mechanics would have been much easier. But so sometimes by reorienting yourself, you can move in a way that wasn't possible. So I think it's extremely productive to also deeply understand our current theories, understand what their issues are, and you know, there are lots of hints that even, you know, in these theories, there's more structure, a richer structure, perhaps different kind of mathematics that can suggest how, in the end, it can be complemented to fully fully rigorous theory. So I think we need both approaches at the same time.
Oh, thank you very much, Professor.
Okay, so it's getting late, but there is one last question from Xiaobin Shen. Can you unmute yourself? The last quick question.
Sorry, I apologize for the last question. I'm just very from the math side. I only kind of discovered what I'm doing sort of like really related to some like physics idea behind. So I'm just wondering, like, apart from this question, is like, what's your suggestion for young researchers who has like no physics background to sort of like pick up some of the intuition? And the other question is that things you mentioned, that the idea is coming from the sense-proven progress. What do you think about like the other paper he's mentioned in his paper from J. Quinn, saying that if in the mathematical world, should we really adopt like this idea to have division of labor, having sort of really separate into theoretical mathematics and the practical one?
Yes. So, okay, so let me try to answer. So let me start with this second question. So you mentioned this work, a paper by Jeffrey and Quinn, that was at some point kind of criticizing the interaction between physics and mathematics. And because they're basically saying, well, you know, before you know, you get sloppy mathematics or you get physics that's not really relevant. In fact, Thurston's paper on proof and progress was a reaction to that. And he basically said, you know, he made the point that the purpose of mathematics is not to give proofs. The purpose of mathematics is to create understanding and or clear thinking, as he likes to say. It's this wonderful phrase that the product of mathematics is clear thinking. And so I think, you know, the frustration, I think, is in two directions. I think, you know, the easy thing to do for mathematicians is to take some of the parts of physics that are formulated such a way that they can understand it. It's obvious that it's related to mathematical issues. But I think, you know, this is a little bit disappointing for physicists. In fact, I think, you know, physicists are really struggling with very, very deep issues. And having mathematicians really be interested in these problems, not necessarily solving them, but at least understanding why, for instance, bringing the theory of gravity and quantum mechanics together, why that is problematic. I think that would be much more interesting. Now, there is a certain risk that you stay superficial, that mathematicians only take the little parts of physics that they can apply immediately, and that physicists only take those parts of mathematics that they can apply immediately. So I think it's like almost getting to know another person. You really want to understand the deep character of the person and the things that really determine what are the questions that physicists lie awake up in the middle of the night, and what are the questions that mathematicians lie awake up. And I think understanding these deep questions would be terrific. I think there's a lot of hope also in the physics community that if mathematicians are interested in our questions, they might provide a fresh perspective. And so I think that's the thing that we should avoid, is only having superficial interaction. So clearly, some of the examples I gave have been very, very productive in mathematics. You don't have to learn all of physics. Like in the enumerative geometry, you can just learn a little bit. But I would say, I would invite any mathematician to really start thinking about the deep problems of physics and vice versa. Have physicists think deeply about what the issues are in mathematics, and just not be satisfied by skimming on the surface, but have a deep dive. That would be my recommendation.
Thank you.
Okay, thank you very much. So there might be some more questions, but it's getting late. It's 9:30 past. Okay, over there. So let's thank Robert for the very wonderful lectures and very interesting discussion here. Okay, thank you very much, Robert.
Thank you so much for inviting me. It was a great pleasure.
Okay, thank you very much. Okay, thank you for staying up so late just before the holidays. So please enjoy the holiday. Thank you very much.
Okay, thank you. Bye-bye.
Thank you. Bye-bye.
Bye. Okay, thank you very much everyone for joining us for this month's